Good morning students, this is Junita Mukherjee once again with the hysteresis curve itself. The topic is hysteresis curve and how we are getting this hysteresis curve, let us see. The representation, the relation between the magnetic induction B and the intensity of the magnetization I of the ferromagnetic material with magnetic intensity H. The graph shows the behavior of the material as we take it through one cycle of magnetization shown in the figure. Formation of the hysteresis curve. The unmagnetized sample is placed in the solenoid and current through the solenoid is increased. The magnetic field B is in the material rises and the saturated as depicted in the curve OA. Okay, so this is it is being risen up and it has been depicted in the curve OA. Next, if H is decreased and reduced to 0, if H is decreased and reduced to 0 at H is equals to 0, B not equal to 0 itself, curve AB. So AB is the curve where we have this particular value. Okay, now the current in the solenoid is reversed and slowly increased. We get a sustained saturation, obtain saturation in the reverse direction at D. The value of H at C is called the coercivity. So now in the current is reduced. Now if the current is reduced, curve DE. DE is there. So the current is reduced here and increased reversed. That is the curve EA. Okay. So E to A is the current reversed. Okay. The cycle repeats itself for a given value of H and B is not unique but depends on the previous history of the sample. This phenomenon is called hysteresis and it is found that the area of the hysteresis loop is directly proportional to the net energy absorbed by the unit volume of the material and it is taken over a complete cycle of magnetization. So what happens to this particular graph is there when we are increasing this particular graph energy, that is the current we are increasing this in the solenoid, what happens? The magnetic field in the material rises and the saturation is depicted at OA. O to A, the saturation is being depicted here and thus H is decreased and reduced to 0. H is decreasing and H height is decreasing and this particular H is being decreased here, which is not the height, it is the magnetic intensity here, the magnetic intensity H itself. So H is the magnetic intensity which is particularly decreased here here reduced to 0 itself. If it is reduced to 0, it means H is equals to 0 itself. If H is equals to 0, then the curve AB will be forming here. Okay, A to B will be forming here. And what happens? A to B with B is 0. So 0 to A. Okay. So the value of B at H is equals to 0 is the retentivity. Now the current in the solenoid is being reversed. The current in solenoid reversed and slowly increased. What happened to the saturation? The saturation direction at D. So it will be decreasing. Okay. Just as it is decreasing away like this. And the value of the C is called the coercivity. Coercivity is called the value of H at C itself. H at C. Okay. So H at C will be equal to coercivity. Now if the current is reduced, curve DE, if the current is more reduced, then what happened to this curve will be reducing from D to E. Okay. And increased reverse curve EA. Increased reverse curve E to A. Okay. It has been decreasing and then increasing E to A. And then what happened to it? The cycle repeats itself for a given value of H, but B is not unique. For a given value of H, it will again repeat itself. Okay, it will go back to saturation point B to A, and then again moving from B to H, and then again moving from H, D to E, and then E to A. Okay, then what happens to this? But depends on the previous history of the sample. So depending on the previous history of the sample, this phenomenon is called the hysteresis. And it is found that the area of the hysteresis loop is directly proportional to the net energy absorbed by the unit volume of the material. So it is being found that it is directly proportional to the net energy absorbed by the unit itself, which is the volume of the material, and it is taken over a complete cycle of magnetization. So particular complete cycle of magnetization is being taken and the energy so absorbed by the specimen appears in the form of the here energy. So here energy in the form of, we will be able to get this particular specimen, and the hysteresis loop for soft iron is larger and narrow, while the hysteresis loop of the steel is short and wide. It will be short, the hysteresis loop will be short and wider, and this will be more narrow. Steel is more narrow. Okay. So from the hysteresis loop of the soft iron and the steel, we can say the retentivity of the soft iron is greater than that of the steel itself. Retentivity will be greater in soft iron, and in case of steel it will be less. Then soft iron is more strongly magnetized than the steel, as we know that soft iron will be strongly magnetized as its core is soft iron. Okay, and coercivity of the soft iron is less than that of steel. Coercivity will be less. Okay, the reverse direction current, if we give, it will be the low in comparison to that of the steel itself. And as a hysteresis loop for soft iron is smaller than that of the steel, therefore hysteresis loss in case of soft iron is smaller than that in case of steel. So hysteresis loss in the soft iron will be smaller in comparison to that of the steel, because hysteresis loss in the steel will be more narrow and wide, as it is given in the diagram itself. So hysteresis loss in the case of soft iron will be smaller in comparison to that of the steel itself. So hearing loss will be more. So this is what we call the hear energy, and hear energy is defined by the hysteresis itself. Okay. So this is how the hysteresis curve has been explained to you. So looking forward for yet another topic in the next session. Till then, take care and stay fit. Thank you.